That's just a kind of a talk, right, where you have liberty to speak and you can share some ideas. But lots of things happened over time. It was not just him, but there were other people, many more people who were doing things at that time. So if you look at a timeline from this book, so there are lots of work, especially in World War II, which was happening on radars for military application. Because if you know radar, if you know any devices, they have 555 in it, right? Crystal, a timing circuitry, a timing IC. So that's where we started with crystals long time ago. In 60, they started what you call as planar batch fabrication process, and that will be the topic of next homework and the paper that I will assign as well. So planar fabrication is that we use what we do today, basically. We use flat silicon surface wafer and we build plane by plane. In 64, they came out with MEMS devices. Now again, what is MEMS? Micro electromechanical systems. MEMS are micro scale devices that have moving parts. What is the fundamental moving machinery that we encounter in everything? Give an example of a moving machinery that we encounter in everyday life.
A clock, maybe, like
Clock,
an analog clock.
clocks, right? So in a clock, there is a motor. We encounter motors everywhere, right? So the principle of motor is, we all know, there is a rotor which has winding and there is a stator which has winding, right? We apply uh, alternating current, and current rotors move to catch the circulating field motors. So we make miniaturized motors, micro scale motors. Can you think of where we want to use motor, micro scale motor?
Well, a microscale motor,
Yeah.
Specifically in biologic terms, surgery. Like let's say right now they have invented a thing where they can remove artery clogs by inserting something in you and then manually getting to the clog and then expanding it and pulling it out. So if you have a motor that's that small, you don't have to actually be that careful and have that steady hands. You just
Right.
inject it and search for it and then extract it.
Right. Yeah. So you think of any invasive instrument that always have a moving part, rotating part more precisely, right? So if you think about motors, you look around, motors are everywhere. Starting from your cell phone, which basically has a gyro or a inertial meter, which we call them accelerometers. And what they do is they can figure out the orientation of things. Right? So everything that we look around has, especially our devices, have motors in it. Micro scale systems that can actuate, that can turn, that can move. So that's MEMS. We'll talk more about MEMS. But MEMS is also not new. As far as 64, they started using MEMS devices. And then we had what we call microprocessor. So if you look at it, in 11 years, we had a microprocessor invented, but not at that scale. But that started increasing the demand of integrated circuits. And they were, if you have an old, really old radio, TV, you would say they brag about transistor radios or transistors. So transistor was a big thing that came because now you could, instead of having it used to be a tube of a transistor, but now you could make it on the chip. So 79, big breakthrough, micro machine accelerometer. And today we have accelerometer in everything, in your car, in your phones, in your iPads, in your whatever gadget you use. Your uh, even your mouse have some motors and some actuators in them. There's there was another debate that started few years ago, not few years ago, but 30, 40 years ago, which was that can we use molecular manufacturing? So this was Eric Drexler was another scientist who, and it's still debated, he published a paper where he talked about using proteins for molecular manufacturing, and debate started that is it doable, is it not doable? We are still debating on that, by the way. Molecular manufacturing. Can we make devices that can manufacture further things by itself, whether natural or whether synthetic? If you see, we're talking about making things, but here came 1982, a major breakthrough, what we call today scanning tunneling microscope. We'll talk about this in detail, but essentially we created a microscope, which was basically a nanoscope, where we could see things at atomic scale. And that changed, and they got Nobel Prize for this, for STM. We call it STM. And then lots of things we have talked about, looked at buckyballs already. Another microscope called atomic force microscope, which is a variation of STM, came carbon nanotubes, and and today we'll talk about nanoscale nodes, nano nodes, what we call them, to quantify or to understand the size of devices where we are. But let's look at couple of things of how we look at things. So what we call as uh, how do we see or how do we understand nano world? One is touch. Touch is again an example of braille code and having small fingers so that you can feel. So we use similar concept where we have very sharp tips. We fabricate very sharp tip. Here is this example for a very sharp tip. And then we would drag this tip on the surface of the maybe a wafer or wherever we have the nanoscale features. And once the tip drags on, and once it encounters the features, goes up and down. That's what is shown in this cartoon. And that movement up and down plus the XY location of that feature is recorded in computer and we get a picture made. So we call these kind of microscopes as scanning probe microscopes or SPM. And then there are two types, STM and AFM. But one way of looking at nanoworld is touch. The other way to look at nanoworld is using electrons. There are two ways how we use electrons. We either throw a bunch of electrons, a beam on the surface, and we see the reflected electrons and we capture those reflected electrons. So we don't flood the surface, we basically use a very sharp beam and we scan the surface. And electrons, when they bounce back, we capture those and they tell us what is there on the surface. That's the thing called scan the electron beam, scanning electron microscope. The other way is that if you have a very thin material, very thin kind of a sheet, we can transmit, we can throw a high energy beam of electrons and they can transmit through. And on the other side, we can measure the once the electrons change the medium and they bounce off the atoms of that thin layer material, they're bouncing off because it's a well-ordered structure. We can exactly see where are all the atoms in that samples. So that's where we transmit high energy electrons. So we call that kind as a transmission electron microscope. And we write them as, we'll talk more about these as well later on, but we have two types, what we call transmission electron microscope, TEM, or SEM, scanning electron microscope. So again, the idea is that over time, over the last 40, 50 years, we have been able to deal at nanoscale to take advantage of nanoscale properties because we have been able to handle them, look at them, or play with them. And these are two approaches how we do that. We touch it or we use electrons to do that. There's another variations where we use ions also, but they are same principle like these. Now, going back to the history, the major breakthrough or the major breakthroughs have come over time by electrical engineers, by device people, by making transistors and then integrated circuits. So hence we have a kind of uh, we have been ahead than the rest on in nanotechnology. So the history, they created the first transistor back in 1947. And this was a group of people, Bardeen, Brattain, and Shockley. And it was a simple thing where here's a better picture of that I have, where they put some material, they put the third terminal, and they could measure the current, the change in the resistance. So transistor is a three-terminal device. We know resistor, right? Everybody knows resistor. Resistor has one unique resistance value to it. 10 ohm, 10 kilo ohm, 1 meg ohm, whatever. But transistor is a device where you have a third terminal with which you can change the resistance of that resistor. So basically by what we call on and off, you can, when you say off, we increase the resistance dramatically. There's no current can flow. When you say on, we basically change the third terminal so the current can start flowing. So that's the whole concept of transistors. So they came up with this idea that we can have a three-terminal device where you could control the current flow between two terminals by controlling the current for the third terminal, hence the transistor. So that was a long time ago, 56. And then they kept on pushing. So there is another group, which is what we know today as Fairchild 8. Some of them went on to uh, found Intel also, but that was the group who worked hard on how do we make this kind of thing into a planar surface, into within a chip, that you don't have to have this whole kind of three-dimensional thing. So they pushed things really forward, and by 60, they had come up with this lower right-hand side. And interestingly, we are still doing things by this procedure, which is shown on the right-hand side. Started from 60 until what it is, 2020 now, we are still doing things the same way, 60 years. But now, instead of just one layer, we are doing multi-layers. I'll show you an example of that also. So, okay, now just a simple transistor. Okay, you still, if you do breadboard, you know that you put transistor, you have to put capacitor, you have to put resistor, you have to put whatever components go, right? If you guys have done breadboard, all of you, right? But now, what if, so integrated circuit is that instead of having discrete components, can we put these all together in one chip? Hence the concept of IC. So where we don't want to have separate things. So this is 1958 lab notebook of Jack Kilby, where he was showing, okay, different connections to a bulk thing, which is shown here on the top right. So you see 4 connections to a bulky thing where he had maybe capacitor, resistance, all those things. That was the birth of IC, and it was done in Dallas. It was done in Texas. Now, there are people who say, okay, much of the technology came from Germany and at the end of Second World War. But if you look at the time, there are lots of things that were developed in USA. It may be based off of that, but still, this is now Jack Kilby got a Nobel Prize because by that time Bob Noyce, I think he had passed away, so they don't give Nobel Prize, those who have passed away. And Jack Kilby, they say he was probably one or two of those who got Nobel Prize in physics who did not have a PhD. He just had a master's. But this was the major breakthrough. One layer, and today we have multiple layers, layers over layers over layers over layers on a chip. We just don't have one layer of circuit. And these are old pictures. These are not new pictures. These are pictures from covers of books. The left-hand side shows you uh, things which are running between two layers, which is these copper wires, right? So these are basically connecting one layer with the other. So the green area that you see open are basically layers where you would have devices built up in that layer. So this is one layer, it's another layer, and those layers are connected by these vertical running copper wires. If you look at in 3D and you etch away lots of dielectric is insulator. If you remove the insulator material, the right-hand side picture shows you different levels of chip uh, circuit that's built on top of each other. So we have multiple layers of things that we made. And hence we can, this was 130 nanometer, which you call 0.13 micrometer. And if we do that, what we end up is we get, this is another view from the side where you see lots of layers. Oh, this is from the top. This is heat sink, and then you have all these things that are connected with each other. So now we can pack how many? 54 billion transistors. There are a bunch of things given on this page, which I hope we will understand today, some of these. So we have so many transistors, and we are using 7 nanometer technology made by Tech. It's not Texas, it's Taiwan Semiconductor Manufacturing Corporation, built by Taiwanese company. But of course, they contract, they are manufacturers for US companies. They build for everywhere. Now, this is something which has been pushed by many different companies. Intel is there, AMD is there, uh, NVIDIA is there. So they're graphic processing companies, right? So now even Amazon is there because they're making their own servers. So there's so many companies, they're building their own chips. There's for many cell phone companies, you know who makes the chips for cell phone companies?
Something Dragon.
It's Qualcomm, the company. They may have, Dragon may be the chip name, but it's Qualcomm, which makes chips for your cell phones. And even iPhone, I think, uses Qualcomm chip. Now, this is Apple A8 processor, which is an old processor. It's not new, it's from 2015. So now we make a design where we have the ICs, we have GPUs, CPUs, so bunch of processing units that come together. So each chip has billions of transistors, then we have multiple chips on the circuit, right? There's this thing written here, ITRS lower bottom, we'll talk about it. So there's a consortium of companies, all the big different players, right? Intel, Qualcomm, Global Foundries, AMD, NVIDIA. So they have a consortium where they come together and they define some goals for next 10, 15 years. That where do we want to go? Where does the industry go? And this happens, they don't necessarily share how will they get there or what is the technology they are using, but they share some numbers, some goals with each other. And those goals go into defining your processor sizes, your accelerometer, so all the things that may go into a simple circuit. So here is a simple circuit showing you an Apple cell phone circuit, right? And you'll have the battery there, so you have the RAM there, you have the antenna, you have lots of things. This push to uh, how small we make or how many transistors we make came from what we call as Moore's law. So Moore, if you remember, he was one of the Fairchild 8, those 8 people who started a semiconductor company. You'll read about this in this homework this week. And he wrote a piece in a in a magazine, electronics, and he just speculated about 10 years. It was in 65, and he said in 10 years we will squeeze more chips on a single silicon chip. And he made a table, handmade table. But what happened was this became a goal. This became what we call today as Moore's law. He was just talking about 10 years in 65, but somehow we picked up these numbers and we said, okay, in 10 years from that time, 65,000 components meant that the number of components would be doubling every 18 months. So this is what it became. That from that prediction, just for 10 years, we took it and the whole industry, they followed it to the letter, and it translated into doubling the number of components every 18 months. That's Moore's law. If you ever hear about Moore's law, remember it was nothing but a 10-year projection in 65, but we took it as industry and we said, okay, we'll keep on following that trend. And even up to probably 10 years ago, we kept on doing that. Two implications, two things happened. When you had to put, like you had to double number of components, you have the same area of the chip, which means you have to make things smaller. All right, so you have to make things smaller. That turned into what you call nanotechnology. One thing, that's what happened. Number two, when we built things so small, the 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 functionality of the chips went up. So now we could have more storage, higher processing power. We could take it mobile, like we have become mobile today. So these two things happened because of following the Moore's law. So again, if you ever encounter these two slides have the answers about Moore's law, that his original claim was this, that unit costs are falling, the component uh, will, the price will, the components, we will put 65,000 components in 10 years, which translated to doubling the number of components every year and a half. And hence, we are here where we are today. Now, to push that, something that we had to do was scaling. We need to make things smaller and smaller and smaller. Now, if you have just a resistor and you want to make it smaller, that's easy to do. But now if you have a whole network of resistances, capacitors, inductors, transistors, that's a major challenge because different devices have different uh, the features that we need to know. But overall, we kept on the trend at a rate of square root of 2. We kept on going smaller. How much is square root of 2? How much is square root of 2?
1.41.
1.3 or 1.4?
1.4.
1.4, right? So, which means we have been going smaller and smaller by making things 1.5 times less. than before. So that's the push what it shares. The feature size, we started at micrometer here somewhere in 70s, but we went to 90 nanometer by about 15 years ago. And now we are hitting 7 nanometer. We'll talk about that also. So that resulted into what we call disruptive computation. We made things smaller. Up to 2007, we kept on making them smaller, but to keep up with the trend, functionality, to keep up with functionality, we started adding different materials to silicon. We started making multiple core chips, right? You know, Edgar is sleepy. How long have you been here? For a while. So now we are making things in different materials, and we are making things in what you call as multiple core. You know, now we have quad core. We put, instead of just having one chip, we decided, okay, we can have multiple chips. So we can keep on pushing the features, not the features, the functionality. So about 10 years ago, we moved from just to the race of making things smaller to how can we maintain the functionality and keep on increasing the functionality. So that's what happened. But we still have a concept what we call as technology node. You know, we were talking about making things smaller. And so we define a thing. Let me show you the next one first. So technology node we define as the feature sizes. In terms of the feature sizes, we say, okay, this is the technology node. For example, we were making 35 nanometer memory devices. We said, okay, this was 35 nanometer node. If we had 45 nanometer things, we said, okay, now these are real pictures. These are real device pictures from transistors where we can see the atoms. In the lower left side, we can see the atoms. So I'll go back to the definition, but before that, I want to share what does it mean to be a technology node. It means the size in nanometer, that how small are we making chips in that specific time, right? So like we started in 97, we were making things mostly in 250 nanometer size, right? In 1999, we were making things at 180 nanometers. So that's what we call, in 99, we hit 180 nanometer technology node, right? Just a terminology, but it's important for us to know because technology node helps us understand how small are we making things. Because next module, we will look at how we make those things small. But right now, I wanted to see that what is technology. We'll come back to this. Let's go back to the definition of technology node then. It's a standard definition, minimum half pitch of custom layout metal interconnect. Interconnect is, which is basically used to connect one device to the other, right? So you have to put metal layer to, just like you do on breadboard, right? So, but here you have to put a very thin metallic line to connect two components together. So how pitches, how often can you lay things next to each other, right? So if you can park 20 cars in a parking lot and you park every car maybe three, I don't know, from passenger door to other passenger door is maybe, I think it's 8 feet for one car size. So our pitch is 8 feet. But if you have a truck parking lot, maybe the pitch is going to be 10 feet. You understand? Like a parking lot, when you go to a parking lot, there is a standard size of how big is a parking space for one car. I think it's 8 feet from one line to the other line. So which means the pitch is 8 feet. That's how we define pitch. So here it says it's the minimum half pitch. we take half of that number, that how close can we put those metal interconnect lines. That is what defines the technology node. So when we talk to each other, then if you talk about 45 nanometer technology node, we are talking about 45 times 2, it's the double, right? So it's not exactly double, but that's what we call it half pitch. That how close can you make things next to each other? So we use that number to define the uh, high density, or to understand the density of a given circuit. And this comes from here. You make things small, but how close can you make things next to each other? Right? With me on the definition. Now, starting from 97, we have been pushing to go to smaller and smaller technology node. We have just hit 7 nanometer. It got delayed, but now it's coming out in production. We are at 7 nanometer. If you just follow, and you would see there are more and more players into this process. We had Intel, TI, IBM, TSMC. We had Intel, TI, IBM, TSMC. Keep on going. You add Infineon, AMD. You have Chartered. So there are other companies that keep on coming in, and many of them are not from USA. You have Matsushita, Samsung, SMIC, Chartered. We keep on going smaller and smaller. The rest of the world is catching up in making those devices like us. Amara, probably it's time to go. We all are feeling sleepy.